We're going to be dealing with connected body problems, and so we're going to start out dealing with elevator problems. So as you can see, there's an elevator here, and the elevator is connected by cables to a counterweight, and of course that's so that the motor and the cable don't undergo extra strain, and you can run your elevator a lot more safely if you've got an adequate counterweight. So we start out with a frictionless pulley. As usual, we're going to simplify the system as far as we can, and by making that pulley frictionless, we can look at some of the simpler things that we need to do. So let's introduce our elevator, and of course we have a rider, and that rider of course is none other than Isaac Newton. And naturally Isaac has a mass. Isaac and his elevator car have a mass of m1. Next thing we're going to do is have a look at the counterweight that goes on the other side. And of course this is for safety and everything else. So there's our counterweight on the other side, and our counterweight is of course going to have a mass of m2. There we go. So there's our system. It's essentially a connected system of two bodies, and we're going to apply Newton's law to solve the problems that are associated with it. One of the typical questions that you are asked in these cases is, assuming there are no other forces involved other than gravity, what is the acceleration of this system? So if I just let that go, if the frictionless pulley runs, what's the acceleration of the system? The second kind of question that you get asked in this situation concerns the tension of the cable. So provided there's no motors operating, what is the tension in this cable? Now we're going to continue to simplify this system. I find it's not going to be a problem if I assume there's no pulley here. And don't worry, Sir Isaac, we're going to fix this in just a second, you'll see. So I'm not going to worry about the pulley. I'm going to change my frame of reference. It's no different than if Isaac was in his elevator this way, and the counterweight was organized this way, and I have two forces acting in opposite directions, which are essentially gravity with a slightly different frame of reference. So there's my system. I've removed the pulley. Gravity is going to be operating in the positive direction on Isaac's car and in the negative direction on the second mass m2. Now my system is simplified and I can start to apply Newton's law. So there's my Newton's law. The net force on the system is going to be equal to the total mass times the acceleration of the system. My net force, of course, is equal to the force on object 1, which is Newton, and it's going to be operating in the positive direction according to my frame of reference. And the force on object 2, which is going to be operating in the negative direction according to my frame of reference. And of course the total mass of the system is just m1 plus m2. So it's relatively straightforward. We just have to do a little bit of substitution to make this work. So here are my equations. For the net force, I have substituted the mass of object 1 times the acceleration due to gravity, plus the mass of object 2 times the acceleration due to gravitational field intensity, and I've included a sign to make the signs correct. So let's start to do some substituting and moving around here. If we want to find acceleration, we need to isolate it, so let's move the mass over to the other side. Like that. Okay, so I've got my acceleration isolated now. Now, let's substitute our total mass into this equation, and it's going to look like that. And let's put our net force expression into the equation like this. And the last thing I could do to clean this up just a little bit is I could factor this expression a little bit. There we go. So, anywhere on this line, I have an expression for the acceleration of the system given the masses, and of course the implied thing here is gravitational field intensity.